Hi, my name is Zayden. I'm working on this project with Evan, Katie, and Tim. For this project, we decided to go with the strip problem. I'm doing the understand and plan portion of this problem. So for understanding the problem, it's important to put it in our own words. We divided it into two sections, just the problem statement and what we're being asked. So the problem statement, it goes over as this. There's a thin strip that is charged and it exists in the XY plane. It is a very long strip in the x-axis. It has an arbitrary width of 2L that extends along the y-axis. And the strip has a given charge density equation of charge density equals the initial charge density times y over L. That sigma y equals sigma naught y over L. And so what we're being asked in this problem is that we need to determine both the electric field and the electric potential for every point along the y-axis where y is greater than L. So now we need to let v equal 0 and y equal 2L for this problem as well. So understanding the problem, another part of this is the relevant quantities and assumptions, quantities that we need to identify for setting up this problem, as well as any assumptions that we need to make going forward in this problem. So some quantities that we have is that the charge density, we are given this equation in the problem statement. It's that the charge density equals the sigma naught y over L. So the initial charge density y over L. And the width of the strip, we're given that as well. It's 2L. The length of the strip is not given. It's just said it's very long. So it's just important to note that we have that as a quantity. We don't know the x, but it's just very long. So it's going to be important for making an assumption just in a little bit here. And then we have that v equals 0 at y equals 2L. So we know the charge is 0 at the full width. So another assumption, or some assumptions that we can make, is that we know for this problem that we need to identify it at the points that y is greater than L. So we're only focused on those points. Another assumption we can make is that we know this is a 2D problem. We're only dealing with this problem in the x and y axis. There's no three-dimensional. It's not just along one axis. We're dealing with just the strip as a two-dimensional object. So we're just focusing on that. Another assumption that we can make for this problem is that there's no external charges or electric fields affecting this. We just have the closed system with just a strip along the x and y axis. There's nothing affecting this, and that would make the problem a lot more complicated. So luckily we know that we can just assume that there's no outside electric field or charges that are going to affect the system that we have. So as I mentioned earlier, we don't know the length of the strip. We just know that it's very long along the x-axis. So for this, we're just going to assume that it's an infinitely long wire. This is going to really help us in our calculations as well as the setup of the problem. Just knowing that certain value that we can assume that it's an infinitely long wire with 2L.
This now brings us to our physical representation. We can put our physical representation on XY coordinate frame. As you can see, the wire is located at the origin, where we have a distance of L in the Y direction upward and a distance of negative L in the Y direction downwards. This wire has a charge density of sigma naught Y over L. Our distance Y is from the origin or the x-axis to the edge of the wire. And then our distance D is from the edge of the wire to our point charge. Our point charge is labeled by P. The charge distribution and electric field diagrams. On the left, we have the charge distribution graphed on an XY coordinate frame. As we get farther away from the x-axis, our charge density will increase, and as we get closer to the y-axis, it'll decrease. In the positive y direction, our charge density will be positive, so we have positive charges, and in the negative y direction, we will get negative charges. Our electric field diagram. This diagram, as seen on the inside of the wire, as we get closer to the y-axis, our electric field will be greater than farther away from the y-axis. This is because we're taking a point on the y-axis and not a point anywhere left or right of the y-axis. On the outside of the wire, because the charges in the positive y direction are positive, they will repulse, which is shown by the arrows pointing away from the wire. Oppositely, on the bottom, in the negative y direction, the arrows will point inwards because negative charges attract. Calculations for the electric field. First off, we can start out with the electric field calculation of a line, which is equal to 2k lambda over r in r hat direction. R hat is equal to y hat because we are only dealing with a point charge on the y-axis, so our electric field will be in the y direction. R is equal to p minus y, where p is the point charge and the distance from the origin to the point, minus y, where y is the distance from the origin to the edge of the wire. Sigma is equal to sigma naught y over L, which is our charge density of a plane equation. Using math, we can find that lambda is equal to sigma dy. Plugging sigma dy in for our lambda, we can then see that dE is equal to 2k sigma naught y over L over p minus y dy in the y hat direction. Integrating this, we can set our bounds from negative L to L, which is our width of our wire. And we can simplify this integral to make it easier on ourselves by pulling out all the constants, which is 2k sigma naught. Then I use Wolfram alpha to calculate the electric field, which then we can see E is equal to 2k sigma naught over L, P natural log P plus L over P minus L, and that is subtracted by 2L, and this is where P is greater than L. If P is less than L, this would not work because our natural log would not work because it would be negative. Simplifying this equation further, we can see that our electric field is equal to 2k sigma naught over L, P natural log P plus C minus P natural log P minus L minus 2L, and this is still where P is greater than L.
All right, so now that we have calculated our calculations for the electric field, there's other aspects to this, specifically because it is an integrated problem in which we are calculating that electric field along a distance that is arbitrary. And so this brings us to our calculations of electric potential. The relation between electric potential and electric field is really interesting because while usually you might calculate the electric potential in this equation that we can see here, where it is equal to our Coulomb's constant by charge divided by the distance of separation. However, we can also calculate the electric potential using the electric field by taking the integral of it and then multiplying that by delta V. And this, in this case, would be delta length, and that is simply based upon what we can see up here, where we can see the electric field is related to the gradient of the potential. And so when we rearrange that equation, we can use the electric field to calculate it. Because we were given symbolic answers for this or numbers, we can then use that in this equation, and then we can really just apply it here. It's basically just plugging in the values, and this is what that pre-integration would look like when solving for the electric potential.
Making sense of electrical field. Bringing over our electrical field equation that we got previously, we have K, a K constant, in this equation. K is equal to 8.99 times 10 to the 9th Newton meters squared over Coulomb square. Plugging all these units into the equation, we see that we have electric field, which is Newton meters per Coulomb, which is equal to Newton meters squared over Coulomb squared columns over meters squared over meters. And then in the parentheses, we get meters minus meters minus meters. Canceling out all these units, we see that Newton meters per column is equal to Newton over column times meters, which is equal to Newton meters per column, which is equal to Newton meters per column. So our units check out.
So when it comes back to our electric field, we really want to make sure that everything that we've done is correct. And so there's a few ways to check that. And one of the number one ways to do that is by referencing the entire equation and looking at what each part does specifically. So in this case, we know that electric field will decrease in magnitude the further we are from the source. This is just a simple diagram in the case where it's a positive for charge. And we can see that essentially in the closer proximity, we have larger vectors representing larger magnitude of the electric field. But the more we go out, the lesser that magnitude of the force of the field is. And so there's a few different ways that we can also since make this further. And how can we prove that? So first, in our equation, we knew that if P equaled L, we would have an undefined equation. This would result in them all canceling out. And also just there would be no content within the value for the electric field. If P were to be 0, then the electric field would be 0. This is seen here in the electric field equation, in which we can plug in 0 for each of our P values. But you'll notice that that simply results in 0. So, and then finally, we also know that K is a constant. That being said, if we look at our equation, we can see specifically here at the beginning, when we have the electric field, we can look at the relation of them, and we see that length is on the bottom portion of that problem, of this equation. That being said, if the length were to increase, we would see a decrease in the electric field, which is what we just said previously based on what we know in regards to electric field and electric potential. By being able to take this into our equation, and again, say we look at this L and say it was a large number, even if it were to be 4, for example, this would suddenly become 1/2. And that would then 1/2 the rest of the entire problem, making the electric field smaller than if L is singular and is 1, and we have 2 in front of our Coulomb's constant. And so by being able to look at the original equation and then relate that back to kind of what we know, we're able to see that it, as an equation, reacts how we would expect it to react qualitatively and how we would expect the model for electric field to look like.
So for our first reflection, we have chose homework 3, activity 3. So in that activity, we went over a straight wire with a length of 2L on the x-axis and are tasked with finding the electric field at a point on the x-axis from the center, which is greater than the length of the wire on that side of the axis. So this problem is similar to what we've been tasked with because the wire has the same width, which is 2L, and we are tasked with finding the electric field of the wire in the direction of that width. In the homework, we had the wire in the x-axis only. For the project, we have had it on the y-axis, and it is infinitely large on the x-axis. Another thing that has been similar was in Thursday, week 4, lecture 8, we went over in class how to solve for the electric potential of a point charge above a uniformly charged line in exercise 2, case C. I have the case on the right of the screen here. You can see the point, a distance y above that uniformly charged line, and the math underneath it to solve for P. So it's similar because you're solving for a point above the line in the y-axis. And in both cases, you're solving for any spot on the y-axis. And you just have to put in the value to find which spot you're looking for. Now it is different because in class, the wire had no thickness. And what we're being asked for a wire that has a thickness of 2L. And then in Thursday, week 5, lecture 9, we talked about using electric potential to find the electric field on a plate. Now they're similar because they both have to do the math to figure out the electric field lines within a system using the energy of that plate or the line. However, in class, we were worried about how far away in the Z it was. In our project, we're worried about the Y-axis. How far is this above the object that we're looking at?